back to a video series on MAT 1033 Intermediate Algebra. This is Sean Perry. We're looking at video 26 in the series on the inverses of functions. Here I'm going to give an introduction to the idea of the inverse of a function and some of its properties. Now, I just want to mention that inverses of functions aren't actually going to be covered in great detail in this course. The reason I'm mentioning it at this time is because this is the right time in the sequence of content to do so, and we're going to use the ideas of cancellation and inverses a lot in the course. So it's worth at least mentioning what they are and how to work with them in an introductory sort of sense. The main thing to keep in mind about an inverse is its property that it cancels a function. So functions have a particular inverse, and if we compose those two together, they cancel each other. Now, what do we mean by cancel? So let's remember what we meant in the context of addition. In the context of addition, if I add 3 to something, but then I also subtract 3, it's as if nothing happened. And by nothing happening, we could also think of that as adding 0 to something. It's that kind of nothing. In the same way, we think of division as canceling multiplication, because if I, for example, times something by 3, but then I also divide by 3, we just get that original something. It's as if nothing happened. But in this case, we could also think of it as timesing by 1. It's that kind of nothing. So in general, then, the inverse of some function f of x, which is written f to the minus 1 of x, cancels a function, f of x, when we compose them. We talked about composition in previous videos. So if I put the function f of x inside the function f to the minus 1, then what we get is the input. Whatever the x was, whatever the original value getting plugged in was, that's what we get back. And it works the other way too. If we plug the inverse function into its original function, we get back just the simple input. Before we continue, I just want to say that this to the minus 1 power is really, it doesn't mean to the minus 1 power. It means the inverse of the function. This is a notation abuse. We're going to talk more about negative exponents in the next video. But for right now, just let me mention that this means the inverse of the function x. So this is a good time to take some critical notes. Please copy these down and show them to me as proof that you watched the video. I want you to know, what does the inverse of f mean? The inverse of f of to the minus 1 of x is the inverse of f of x, if and only if, when you compose them, you just get x back. This composition needs to work both ways, and that's the main idea here. It cancels in this sense, in the sense of composition. Now, when we looked at addition and subtraction, we said that those cancel to 0. In other words, they're the same as plus 0 or minus 0. That's the additive identity, the thing that if you add it to something, it doesn't really change it. And multiplication and division canceled to 1. That is to say, it's the same as timesing or dividing by 1. The thing which, if we times or divide by 1, it doesn't change anything. Okay, so do these f and f inverse cancel to something? Is there some operation or some function that we could consider they cancel to? Yes. So we consider this kind of boring function to be the identity function. It's written here as I of x, and what does it do? It just gives you x back, right? The identity function of x is x. It's kind of a boring function. It just gives you your input right back again. But it's not so very trivial. I mean, if we consider this to be some output y, then what this says is y is equal to x. And this is, in fact, the diagonal line with slope of 1 and intercept of 0. And that's not such a boring function at all. That's an honest-to-God line. So we shouldn't think of this as being completely boring. It's, in fact, a line, and it's actually going to come up later in this video when we talk about how to find the inverse of a function. It's going to have a special relationship, f, this line, and its inverse. Let's take a look. So how do we find the inverse of a function given a function? Well, if f takes an input x to some output y, then what f inverse has to do is it has to take that y as an input and take it right back to x again. We sometimes draw this picture we say that x is taken by f to y, and y is taken by f inverse back to x. So let's say f took 3 to 4. Well, if you plugged in 4 into f inverse, it would have to get taken back to 3. That's what it would mean for f inverse to undo whatever f did. So in this way, the roles of x and y are getting switched a little bit, even though we could set f inverse of x equal to a y and treat that like the output still. This still gives us an interesting way of thinking about it, that the output of one function has to get taken back to the input of the original function. And this actually gives us a hint about how we're supposed to find f inverse. Let's look at that method with an example. Let's say that f of x was equal to 3x minus 2. This is a line. It's also our function in this case. What is f inverse of x? What undoes timesing by 3 and then minusing 2? Well, the first thing we want to do is maybe write this a little bit shorter. Let's, instead of f of x, write y in its place and say that y is equal to 3x minus 2. Now, because we know that the inverse is going to need to switch x and y, let's change them here. Let's change where I see an x, I write y, and where I see a y, I write x. Now we're going to solve for y again, because that's going to be our output. We want this to be undone. We want to get down to this y as our output now and see what kinds of inverse operations would make that so. Okay, so how do we solve for y, right? We're just going to get rid of this minus 2 by adding 2. And then once we do that to both sides, we divide by 3. And now we have this function x plus 2, that whole quantity divided by 3. And that's our new f inverse. That's it. We found this function, f inverse of x is equal to x plus 2 over 3. And remember, that's x plus 2 then divided by 3. If you see the quotient bar, there's little implied parentheses around the top there. You must do this first. Now let's check to make sure that that is in fact the case. What happens if I take this f inverse and plug it into the original f? Well, f inverse, as we are claiming, is x plus 2 over 3. If I plug that into f, well, what was the rule? What are the rules for f? It was times it by 3 and then minus 2. So if I times by 3, that's going to cancel with this divided by 3. And then minusing by 2, that's going to cancel with the plusing by 2. And that just gives us x. So that's it. That's the inverse. They canceled. Likewise, if we compose them in the other order, if we put f of x into f inverse, that's plugging the rules for f, 3x minus 2, into f inverse, which is minus by 2, and then divide that whole thing by 3. And now, sort of canceling in the other order, we first get rid of the 2's up top, and then we divide off the 3's to just give me x. So both compositions just yielded an x, so we found inverses. Let's summarize that as some critical notes. How do we find f inverse given f? First, write f of x equal to y equal to the rules for f of x. Then switch everything around. Write x where there was a y before, and write y's everywhere you see an x in the rules. Then, if possible, if this is going to work, we'll use our rules of algebra to solve for y again. And once we manage to solve for y, we will get f inverse. Let's explore a little bit more about this example that we just found, that these two functions, 3x plus 2 and x minus 2 over 3, are inverses of each other. Let's plot those together with the identity function. Now, you might notice, looking at their graph, that we have, well, first of all, how do we graph them, right? There's, these two are lines. This is 3x plus 2, so intercept of 2, slope of 3, over by 1 up 3. And this one, if we distribute that divide by 3 against the x, that's a third of x, and against this 2, that's minus 2/3. So this has a y-intercept of minus 2/3, something like this, and a slope of 1/3, over by 3 up by 1. Okay, so let's graph those, and let's graph y equals x, the identity function line. Take a look. I mean, there's this pretty interesting relationship, right? I mean, first of all, they all hit at the same point. That's not normal for 3 lines. But more than that, They are reflections. The purple and yellow line are reflections over the green line. And that is the case. When you interchange x and y, what that does is reflect over the line y equals x. That is the geometry of what's going on with inverses. They are reflections over the y equals x diagonal. So just to recap, as we said, they all hit in the same place, but more than that, they are reflections. You can try this for yourself. Try taking a point x, y, 3, 4 if you like, and then writing its interchange of y and x, 4, 3 if you like. And what you will see is that they are in fact reflections over the diagonal line y equals x. So that gives us a geometric way of thinking about the inverses of functions. And this, right off the bat, has some important consequences. Let's consider another pair of functions. Let's consider x squared. We've looked at a graph of x squared before. It has this parabolic shape. And let's consider its inverse. Now, what would its reflection over the line y equals x be? Well, it's this kind of sideways parabola. But wait a minute. I mean, what x squared here, this passed the vertical line test. This is a function. But this thing over here, whatever it is, it doesn't seem to, right? Something has gone wrong. This has now failed the vertical line test. It is a relation, but not a function. So what we've seen is that a function might have an inverse that isn't a function. Interesting. So this actually brings up something. Because we are interchanging x's and y's, what we're doing is interchanging horizontal and vertical lines too. And this means that if f of x fails the horizontal line test, and there's a few different words for that. We sometimes say f of x is not one-to-one, or f of x is not injective. Whatever that means, it means that there's a horizontal line, as opposed to a vertical line from before, that f of x passes through. Specifically, that means for two different x's, you get the same y value, the same f of x. That's what it looks like when a horizontal line passes through the function f of x. And in that case, the inverse is not a function. The inverse fails the vertical line test when f of x fails the horizontal line test. This is worth some critical notes, so please copy this as well. Sketch this graph. If f of x fails the horizontal line test for some horizontal line y equals a, then f inverse fails the vertical line test at x equals a. Here you see the interchange of y and x. So that means if f of x, which might be a function, fails the horizontal line test, then f inverse of x is not a function. It's only a relation. It fails the vertical line test. Now, we're not going to talk much more about this inverse of x squared in this video. We are soon. We're getting there. We need to talk about exponents first a little bit more heavily, and we're going to do that in the very next videos. But for right now, let's just keep in mind that whatever its inverse is, the full inverse of x squared is not a function. And let's just note that with this example. If I took -2 and squared it, I'd get 4. If I took +2 and I squared it, I'd get 4. And so now if all I do is I tell you x squared is equal to 4, we don't know. We don't know whether or not x is equal to -2 or if it was equal to +2. Both of them are solutions. And asking one question and getting two answers back is the hallmark of not a function, just a relation, not something that we can apply our properties of functions to in its entirety. We have to be very careful about these kinds of things. We'll talk more about how we can restrict our view, restrict our domain, so that we can pick clearly one of these two answers. But for right now, I just want you to see that inverses of functions, just like subtraction is weirder than addition, and division is weirder than multiplication. You can multiply by anything, but you can't divide by 0, okay? Well, inverses of functions are in general more complicated than their function counterparts. We have to keep in mind that as we ask the inverse question, we might get into this sort of more complicated terrain. And that's okay. That's where math really gets fun. So don't be scared, but we proceed with caution. So now I have some praxis exercises that I would like you to do. For this, I'd like you to simply assume that f passes the horizontal line test, and so its inverse is nicely defined and is a function. For problem number 1, anyway. For the other two, I leave it up to you to figure that out. It definitely isn't true for this fellow here. I mean, this definitely doesn't pass the horizontal line test. But for problem number 1, assume that it does, and then see if you can figure out these problems here, 1, 2, and 3. Take a moment. Okay, let's see how you did. So for problem number 1, if f of 2 is 6, then f inverse of 6 is 2. If f takes 2 to 6, f inverse must take 6 right back to 2. That's what cancellation would mean here. And likewise, if f inverse takes 3 to 9, then it must be the case that f would have taken 9 to 3. That's what cancellation in this direction would mean. Let us find the inverse for f of x equals 2x plus 3 over 4. First, we write function in y equals notation. Then we switch x and y. Wherever I see an x, I put a y. Wherever I see y, I put an x. Now we solve. First, let's get that pesky 4 up off the bottom. Multiplying on both sides by 4 should do that. Now let's minus the 3 over and divide by the 2. Once we do all that, we've solved for y. That's our f inverse. So 4x minus 3 divided by 2 is your answer. If you like, you could write that as 2x minus 3 halves. That would totally be fine as well if you wanted to distribute that division by 2. Finally, let's take a look at this function that isn't one-to-one. It does, in fact, fail the horizontal line test here. But what about at A? What was the question here? The question is, well, the question, I've forgotten a symbol right here, so let's put the right symbol in. This is more asking you to interpret what A inverse does. If f takes A to B, then f inverse must go back the other direction and take B to A. So the question of what do you plug in here to get A, you must plug in B. All right, that's it for this video. Thank you for your patience. Good luck with your studies, and I'll see you in the next one where we will be talking about the properties of exponents. Have a great day.